We can start right about now. So I think, okay, so maybe I will put this on the chat, but essentially the structure of the presentation is going to be, so which we present for about 30 to 45 minutes. And after that, we'll have questions until there's no more questions, and then we call it a day. So that is going to be the structure of the presentation. So having said that, actually, I realized I haven't actually introduced Ulrich. So Ulrich spent a couple of years doing his undergrad in computer science and physics at Rose University, and then from there he moved to so he did that at the University of Boya, in Cameroon. And then from there, he did his master's and PhD at Rose University in South Africa. Actually, I was there doing my bachelor too while he was doing that. So we were there together during that time period. And then after that, he did his postdoc in the radio astronomy group at Rose University. And now, after that, and since then, he's been working in machine learning at InstaDeep in South Africa, in Cape Town, I think. So I think that's pretty much it. And so he has like a whole bunch of experience, both in physics, in computer science, in radio astronomy. So it is awesome to have him here presenting to us the research that he did at InstaDeep. So without further ado, thanks Ulrich for coming here, and thanks for presenting.
Okay, thank you, Joe, and thank you to the organizers for giving me this opportunity to present my work to the KmerAI community. Yeah, so the work is titled Generative Model for Small Molecules. It's a project we've been working on for the past few months, and the idea is to build a foundational model to generate small molecules with specific properties. So the project is kind of like the leader on the project, but it's kind of a collaboration with like different colleagues at InstaDeep. And we recently actually kind of presented it at ICML at a workshop on foundational biology. So kind of the structure of the presentation is mostly going to be like in 3 sections. It's kind of like a motivation section, or I kind of like try to explain a little bit the context. So I try to make this the presentation more around like how applying machine learning in this field, and not too much of the mathematical and theoretical details. And then there's going to be a section around the methodology of what we did, the methods we used, and the results you have. And then finally, we're going to conclude with ongoing work and the bigger scope of the project, and how the vision you have for this research. Okay, so drug design is quite a lengthy process. Generally, the procedure which we go in order to design a new drug is generally a very long period, and there's so many stages. So literally, this graph is kind of like a little bit of just a summary of kind of like the few phases that a certain compound goes before you can finally be accepted as a drug. And literally, as you can see, like a bunch of arrows here just indicating the fact that a lot of these stages are repetitive. And generally, they kind of like, it requires a lot of experiments. So you generally have what you call in vitro. So there's a kind of experiments that are done like outside of a living body. You have in vivo experiments within living body, like human beings. And in silico are usually computer experiments. So the process is very lengthy. It's time consuming, as I said already, and it's also very expensive. And mainly because like the way to search a new compound is literally just to explore all possible compounds and try to find what fits the property we want. And approximately like they estimate the chemical space of all possible compounds to be roughly around 10 to the power 60. So that's quite a huge space to search. And usually, so there are different ways of doing it. And then recently, over the past few years, there've been a lot of like developments in computer-aided drug design, and also currently now with the range of success we're having with the machine learning. So there's kind of a lot of research in that direction with using generative AI, and the process at least to try and accelerate this process, find ways to have machine learning models that can actually produce candidates that can maybe skip certain stages in the drug discovery cycle. Okay, so in the context of this work, probably going to be talking about two things. So you have what you call a ligand. So in this context, a ligand could really be defined as so many things, but in this context, we're going to define a ligand as a small molecule. So it's a small molecule, and this is what we're trying to find. So whenever we're trying to develop a new drug, is we're trying to come up with a new molecule, which is going to call here a ligand. And in the drug discovery process, you have what you call a target organism. So generally, whenever you want to find a drug for a new disease, you need to identify the disease in the body that this drug needs to affect. Most of the time, it's a protein. And then the idea is to find a drug, a molecule that is going to bind well with that protein in such a way that it modifies the properties of that protein. So that's roughly like my lightweight explanation of how the chemistry of curing people works. And that is why the process of discovering a new drug is quite a lengthy process, because you need to find molecules with specific properties in terms of just the toxicity, and there's a broad range of properties that it needs to pass. But then also you need to predict how the molecule you find will bind with the target protein you want, and that's a very difficult process to do. So generally, we call that process molecular docking. So like on the right here, you have like this animation. So molecular docking is the process where you try to find the conform. They call it the conformation. So that's literally the the way in which the molecule will bind and fit into the target protein. And for now, there's not like a clear way to do it. Most of what we do is like the kind of like physics simulations that try to estimate the kind of mechanical forces and energy that's going on to find the most stable way in which the two molecules could bind together. And so before you kind of like come up with a new drug, you need to be able to predict this conformation, because this conformation is generally the way it's measured is measured in terms of what you call the binding energy. And you want the molecule that will bind well with the target organism. Yeah, so that's kind of like, so the takeaway is like we're trying to generate small molecules which are called ligands, and we want these ligands to bind well with specific target proteins. Then in the field of machine learning, the way we've been doing around is they've kind of like three broad range of categories of models for molecular generation. So you have sequence-based models. So literally sequence-based model. These are models that are based on the concept that you could represent the molecule in a string-like fashion. So if you could do this, then you could use sequence models like recurrent neural networks or transformers. And then so this relies on finding like the best representation of the molecules. So here I'm just illustrating like three possible representations that exist in the field. Then mainly you also have graph neural networks. In this case, you represent the molecule as a graph where you have like the edges being the bonds between the atoms, and the nodes are those atoms. So that's one approach. And then there's the structure-based prediction, which uses mostly equivariant neural networks. So in this case, these are mostly neural networks. So we're trying to preserve different sort of rotations and symmetries in the structure of the molecule. Overall, so generally, like most of these approaches have their advantages and their limitations, but generally, like it's kind of like you have to, especially like both, in my opinion, both the graph neural networks and the structure-based neural networks, most of them they also require like a lot of a lot of knowledge in terms of chemistry to be able to design these algorithms, and the sort of biases you put in your model. So for this work, we've kind of like decided to go with the sequence-based approach for a few reasons. I think like probably like there's a lot of studies about transformer models mainly and sequence-based models at the moment, and also there's kind of a broad amount of data for this. So kind of like that was kind of the motivation for going with these approaches. But then, in going with these approaches, the first challenge is to find out the best sequence representation you want for your molecules. So here's an image from a paper. The citation is down there, kind of the reference to the paper is here. And this representation, this kind of the most popular representation that you use for molecular representations, is called the SMICE notation. And so in the SMICE notation, you will represent a molecule in this way. Generally, there are two things to note here. They use numbers to represent like branching points. And then so literally when you have like if you have like a letter, a number like 1, you need to have another corresponding number 1 at certain point to indicate that that's where there's a bond. That's where like this branch ends at this point. So the 2 will match with another 2. And intrinsically, these numbers could be 3 and 3 or 4 and 4, and that will still be the same molecule. So there's not like a stringent approach for this. So this makes that one molecule could have different SMICE representations. And also there's no specific ordering in this. Like you could start from any point and start representing the atoms and have a representation of the molecule. And you could start from another point and have another representation of the same molecule. So there's no uniqueness in the representation. And then the branches and the rings, so the numbers, they don't have any specific constraint. So this actually makes it quite difficult from the experiments we did for machine learning models to be able to generate these SMICE representations in a quite robust way, and also so there's the issue of like actually being able to generate a syntactically valid molecule. Because if you generate a molecule that has like an open ring, you have like a 1 at some point, and you don't have a corresponding closing ring another point, that molecule will not be synthetically valid. So that's kind of the first challenge. And the second challenge is actually once you start generating synthetically valid molecules, you also need to be able to generate molecules that are actually chemically plausible. Because a synthetic valid molecule is just one that represents the syntax of your tokenization and from which you can generate a graph representation of the molecule. But then the molecule actually needs to be some molecule that is, in terms of chemistry, that's chemically possible, like the energy between the atoms should be something that is stable. And that's kind of like another challenge with that. And then finally, after the molecule is plausible, does this molecule have the desired properties you want? So that's kind of the goals. That's kind of the goal we're trying to achieve. And then after the SMICE notation, so the other kind of like string representation that was quite popular recently is what you call the selfish notation. And the selfish notation tried to solve the issue of not having valid molecules. And most of the time, like the challenge with SMICE, or the reason the validity was where you had the branching points. So the selfish notation tried to solve that by actually giving multiple meanings to different tokens in the representation. And they came up with like a different new set of rules. And then in this case, the advantage with the selfish notation is that you can take random surface tokens and that will give you a synthetically valid molecule. So because they give different meanings to different tokens based on their position. So at some moment, a token could be representing a branching point, but then if that doesn't make it a valid molecule, they're going to give it a different interpretation in such a way that it fits the description of a valid molecule. So that solves some of the issues, mostly the validity, the syntactic validity issue. Also, surface it doesn't actually solve the uniqueness issue, but then that's kind of like a list of the problems they have with surface. The main point with surface is the challenge of having chemically plausible molecules. So on the right are kind of some of the examples of molecules you have with surface. So when I mean like chemically plausible, is having like what you have here, these large rings. So although these are like molecules that you could represent, but actually having such rings or such long chains, these are not chemically possible. These structures will be highly unstable and it will be impossible to synthesize and preserve such a molecule. So although surface you kind of like make your machine learning algorithm to generate a bunch of valid molecules, they're actually not like useful molecules you could use. Then another approach people really tried for with this sequence representation is to use fragment-based approaches. So the idea was to, rather than trying to represent every compound or every compound in the molecule as a single token, just fragment the molecule into smaller pieces such that each piece is actually like chemically stable compound. And then in this case, it's kind of like what you have like a byte pair tokenization. You have like instead of using like characters to represent the sentence, you use like you tokenize into words. So that was kind of like the latest research, and this also this kind of like really leaped up the field in this area of sequence-based exponential molecules. But then the difficulty with fragment-based approach is that when you start fragmenting, you start having like a very large vocabulary of unique tokens. So this limits the diversity of the type of molecules you have because you have very huge fragments that you can't really modify. All what the machine learning algorithm does is to link at most one, two, or three or four fragments to form a new molecule, and that really limits the diversity of you being able to generate new molecules. So that was kind of the approach. And then recently, at the end of last year, I feel like we then have this a safe paper that came up with a safe tokenization that was inspired by the fragment-based approach. And in my opinion, this was kind of like a game changer in this area. So the safe tokenization uses what you call it uses a fragment-based approach, but then this is how it works. So it fragments the molecules into different fragments. So you have the colors here representing the different fragments. But actually, within the fragments, the molecules are still tokenized on an atom base. So using this approach actually reduced a lot of issues, and it reduced a lot of issues because the branches were actually within very small fragments, and that was machine learning models were able to handle that. And then the main challenge was just to be able to link the fragments together. But then the results of this have been very encouraging, and that's kind of what we decided to adopt for this work, the safe tokenization. Okay, however, from our first experiments we did, the safe tokenization has like a slight issue. It's mainly that it sometimes will kind of get like a lot of non-fragmented molecules, a lot of fragmented molecules because of its inherent representation. So literally, so in their representation, so if I go back to the previous slide, the molecules are fragmented in different groups, but there's still branches that has to link the different fragments. So if you look, for example, in this molecule here, you have an 8 here. So the machine learning needs to be able to also generate an 8 in the second fragment in order to be able to link these two fragments. So if your machine learning model is not able to capture this, then you end up with sometimes generating molecules that are actually that just consists of a collection of fragmented molecules. So this was kind of the issue with the issue we noticed with the safe representation in our work. Okay, so I think that was kind of like a short introduction and kind of like a review and put into perspective what we're trying to do. So again, just to remind, the objective of what we want to do in this research is to be able to generate candidate ligands. And then we're going to go back on the fact that these ligands needs to be able to bind well to specific target proteins. So the approach we went was first approach was to be able to identify the most robust representation we could use for sequence-based model. And then now and then the next two steps is like we need to train a generative model, and we choose it to be a latent-variable model having like an encoder and a decoder, having an encoder and decoder that are both transformer models. And then the next step is to fine-tune the model in order to tailor it towards specific properties. So that's generally how it goes in the molecular generation field. So the first step is always to try to build a model that can generate different types of molecules. And then the next step is always to have like a fine-tuning step, a lot of the time using reinforcement learning that guides the model to generate molecules with specific properties. So I think that's what we're adopting here. Okay. So the first thing we did was to, although you're using the safe, we didn't use the safe algorithm as it is directly. So we used another thing that we kind of used a slight modification of the safe, which we call safer. And the idea was to try and solve the issue of having having a lot of fragmented molecules with a safe representation. And for that, we had to you had to introduce two special tokens that are represented here with at symbols. And instead, so because our concept, so the safe representation does something. Actually, in the safe representation, the order of the fragments are not preserved. So for but actually that doesn't matter for SMICE, for molecules and representation. You don't need to have a specific order for the fragments. You could place the fragments in whatever order you want. But also we decided to preserve the ordering of the fragments. So we removed the sorting of the fragments. I decided to preserve the order of the fragments. And then the main thing was to remove the dependence on the numbers, because these numbers that represent the branches generally is what makes it difficult to be able to capture the branching points, and that leads to unfragmented molecules. So the idea was to fragment the molecules, preserve the order, and use these two specific tokens to represent branching points. Then in that case, when there's an open ring, the molecule should expect the next token to correspond to the matching ring, to the matching point of that open ring. So that was the idea. So literally, so here you have an example of what a smile notation will be, and then you have in the middle what the safe representation will be, and finally you have the safer representation which you use here. And literally, the main changes you see here is that you remove the branching point that link multiple fragments. So in this case, this 7 here was replaced with this token, and the corresponding 7 here was represented with a double at sign token. So that was kind of that was the idea. And then we don't sort the fragments differently. In the safe representation, they just decided to sort the fragments based on the weight of the different fragments, but there's no like that doesn't really affect anything. So you could just preserve the order. So in this case, we preserve the order to ensure that the next token should be linked to the previous one. However, there's one catch with this thing is like in this approach, when you're fragmenting the molecules, because literally when you do fragmenting, so there's an algorithm that you use for fragmenting that's called the Briggs algorithm. When you're fragmenting the molecules, we need to ensure that we don't have fragments that can have more than 3 attaching points. And those fragments are actually quite rare. It's kind of like you just have like an atom that has like 3 connecting points. Those are quite rare, but it's kind of like, so that was just like to enforce a constraint in the fragmentation algorithm to avoid such fragments. Because if you have a fragment that has more than 2 attachment points, then there's going to be like an ambiguity on which one should connect to which one, and then you won't be able to reproduce the exact same molecule. So that's kind of like a constraint you have to enforce in the fragmentation algorithm. Okay, so in terms of model architecture, so as I said, you had a Latin space model, and you have our encoder is a transformer model, and then in between you have a Latin layer. So you have to map the embeddings from the encoder using a mean function and a log variance function to a Latin space, from which you sample some noise, and then you apply reparameterization, and then you pass this to the decoder, which is also a transform model, and then it tries to do the next token prediction and output the generated molecule. We also included an optional per-seller resampler layer. And so this, the idea with this is our idea is like we want to be able to just be able to sample from random noise and generate a molecule. Then later on, when we go for fine tuning, the goal is that you can replace all this encoder section with whatever we want, and then map that to the Latin space, and then get a new molecule. Then in that case, we will be conditioning our generation on whatever is on the encoder side. So in the future work, when you're going to be talking about proteins, the idea will be to replace this section with the protein information, and then have some sort of network that maps that to our Latin space, and then from there use our already pre-trained decoder for molecule generation to get molecules that are constrained on whatever information comes here. So that's why we kind of have like to include a perceiver layer here, just to test the ability of like mapping inputs with different dimensions to the same dimension of our Latin space we want. Okay, then In terms of training the model, so literally, so when the safe paper came, in their training, they had curated a large data set of around 1.1 billion molecules, mainly from two popular libraries in the field. There's a lot of molecules, so it's the Zinc dataset and the Unichem library. So for this training, roughly now we didn't use the entire dataset, we use around 20% of the dataset. And you also filter the dataset because you only focus on small molecules. So yes, small molecules is molecules with like a certain mass. So you don't want molecules bigger than a certain mass. So you had to constrain our constraint was just to get molecules whose tokenization don't go like above 180 tokens. So that was kind of like the idea to trim it to small molecules. And then we tried like different models of different size, but mainly most of the kind of the common parameters was just like both our encoder and decoder have the same number of layers. And then the main thing we kind of play around is the embedding dimension. And that's kind of like in transformer models, that's literally what scales up the parameter size. Like you get a high embedding dimension. So kind of like the results we're presenting here is kind of like the small models we train. So the one with like so the embedding dimension 128 and the one with an embedding dimension 256. Okay, so that was kind of like the pre-training step. So in the pre-training, that was the idea. It was just like train this architecture for next token generation. Just the way you kind of like train a transform model. The main extra term is like you have to add a term for the Latin space stuff the way you do it like in a VAE model. Okay, so after the pre-training step, the other step is like the fine-tuning step. So for this, our focus was to fine-tune the model to be able to generate molecules that bind with specific protein targets. So in that case, for fine-tuning, as I mentioned earlier, we only want to fine-tune the encoder section. So for now, we only fine-tune these layers, the mean and the log variance layers in the first case as an experiment. So the idea was to just input some molecule and see if by fine-tuning these layers, we can output another molecule that has better docking scores than the input molecule. So that's what's like, in this case, what we did for this proof of concept. Yeah, so you have an original molecule, you pass it to the pre-trained model, you want to sample like new molecules around that region, and then you get that to the docking tool. So the docking tool is what does the molecular docking. And when it does the docking, it gives you a docking score. This is generally like a measure of the binding energy that tells you how well the docking score is. And then from there you compare. So your reward, the reward for the reinforcement learning fine tuning is the docking score of the new molecule minus one of the original molecules. I use a very simple reinforcement learning algorithm for that. Actually, it's called reinforce, kind of like just a fitting name for it. And that was the idea. So the idea was to, in order to generate multiple experiences for the same molecule, so you have to sample many molecules for the same molecule to guide the algorithm. And then the docking tool we use is called AutoDockVina. And it's so that's good. So one of the challenges with this molecular docking is that the experiments are quite slow. So it's kind of like so this kind of like what makes it challenging because the docking is actually quite slow. And it also doesn't make it so suitable for reinforcement learning experiments because in this case, you consider it in a proper reinforcement learning setting. We consider your docking tool as your environment. And most of the time, like, what you want is one an environment that runs fast. So yeah, so that was what we did here. And in this case, so in the fine tuning here, you fine tuning for just so every time you fine tune it for just one protein. So if you want to fine tune for different proteins, you need to fine tune a new model. So that's kind of like the challenge with drug design. So it's kind of like there's no generalization in terms of targets. So generally search for a new molecule for a specific target only. So if you need 5 targets, as in this case, then you need to fine tune your model 5 times. Okay, so in terms of implementation details, most of it we implemented most of the model in JAX. Yeah, mainly because instead we get free TPUs from Google, so you have to do it. So you have to do it with JAX. The pre-training stage of the model takes around 3 to 7 days. Because actually, although the model is not very big, it's still actually very challenging to train such a model. So I really don't know how these guys like at Meta and OpenAI had to train these models because you have to like babysit the training because like the CPUs can die every time. So you need to do a lot of checkpointing to be able to resume your training every time something dies. But then the fine tuning doesn't take long. So the fine tuning on the target train takes like around 4 hours. So that's kind of like the good. So you can repeat experiments in the site and run a lot of experiments. Okay. Yeah. So when you're training the model, the main thing you're kind of measuring is the ability to reconstruct the molecule. So like you're training with like a next token prediction loss. So what you're minimizing is just like the it's kind of just like an accuracy or like the loss in the stuff you're measuring. But then when you get your generative model, what you're actually interested is in the chemical properties. But these are not stuff you can include in your loss function. So in this case, you kind of like so we kind of like measure different metrics for evaluation. Mostly like the main thing we generally consider is what you call the QED. So the QED is a measure of how your molecule looks, how likely is it to be like an how likely is it to look like existing drug-like molecule. So it's kind of like a metric. It's generally around it's kind of it's measured on a scale from 0 to 1, and the closer is to 1, it means the molecule you generated is very similar to existing molecules. And then there's what they call the synthetic accessibility. And this is a metric you want to reduce because this tells you how difficult will it be to synthesize this molecule in a lab. So these are kind of stuff that we just use like people like in the chemistry field, like they have like some sort of hard how do you say it hard coded algorithms for estimating these values. And then yeah, so that's kind of the main thing. Then the other metrics are mostly in terms of just like in terms of just the statistics, like how unique are your molecules. So you want the generative model that generates like as much unique molecules as possible, because that increases your diversity and that also increases your chances of like identifying like good molecules or rare molecules. So the idea is like to be able to find that one good molecule. And then the reason we did not use a safe algorithm directly was because we wanted to avoid fragmented molecules. So also the kind of keeping track a little bit of the fragmentation. And then finally the validity. Yeah, we also want to get like a high percentage of valid molecules. So this is also kind of like a little bit, we tried to do a little bit of scaling. So actually the first top plot was just like showing like actually that, yeah, using that safer representation was able to improve, especially the fragmentation rate. I think like, okay, I think the second metric, so that's showing like kind of like able to represent the fragmentation rate. So yeah, just like the first plot is using greedy decoding, and then the other plot is only sampling using stochastic decoding. So in both cases, applying the safer notation was kind of like solve the problem, the main reason why we decided to use that and slightly modify the safe representation. And then in both stuff, like the main important things like the QID scores are actually quite good. So it's kind of like most of them are above 0.6, 0.7. So that's kind of like generally good. So in the next session, we talk about like what we call hit targets. We generally want these values to be like above 0.5. So that's quite good. So that's why like when we went for the RF fine tuning, we didn't bother including this in our reward function. Then the table below just a little bit of summary of the two models, the one with embedding dimension 128 and the one embedding dimension 256. Yeah, so however, like these results they were a little bit not, so they don't show like a clear pattern in terms of scalability. And I think, so I'm going to talk about this a little bit at the end. But overall, like most of the validity is quite good in most cases. You're getting like above 90% validity in most cases. And also in most cases, like we don't have like, you have fragmentation less than 1%. So I think like that this is literally what we wanted to have. So in both cases, like in both cases, overall the result looks good in both cases, and then we're just happy that okay, our model can generate good enough molecules, because I feel like when we started the project working with mice and selfies, our biggest challenge was always like generating valid enough molecules and generating molecules that are chemically plausible. So here, like having good QID scores and good QID scores and high validity rate was really encouraging, and that's literally what we wanted to have at this stage. And in terms of configuration here, so here you have like some models have this P attached to them. That literally means that it's just these are models in which we included the perceiver. Because when I showed the architecture here, yeah, this perceiver layer was kind of optional. So in some cases we use it, and in some cases we did not use it. Okay, then in terms of RL fine-tuning, so here just showing like a plot of the RL fine-tuning. So we fine-tune these molecules to 5 specific targets. The reason we choose these targets was kind of like there was not specific, there was no not any specific reason why we choose these targets. We choose these targets because we wanted to compare our algorithm with the previous paper, and in that paper they had fine-tuned on these targets. So that the main idea, and they had also in their research they had compared with older models. So we just wanted to be like, okay, let us just follow the same approach and then just fine-tune with these targets and follow the same evaluation criteria they use. Maybe this plot are just showing like some of the training runs. So as we are fine-tuning, the docking score is increasing. And then this just like showing one of the runs on one of the first targets, which is abbreviated as JEG2. And then on the right plot, we're also showing like what you want. So as you're fine-tuning, like you have like the percentage of the molecules which docking scores are changing like above 2 and reducing by 2. And like the orange color, like literally you don't want the docking scores to be reducing. So the ones whose docking scores are reducing a very small fraction, and then the one docking scores increasing has a much higher fraction. Okay, so yeah, now this is the final evaluation. So the final evaluation was like, as I said, so we use the same approach they are using this paper. So the idea, what they used was to sample 3,000 molecules to the model and compute the docking scores of the top 5% hit molecules. So a hit molecule is a molecule that so every target has a docking score threshold. So for that specific target, you want the docking score to have a certain value for it to be able to bind well with, for any molecule to be able to bind well with it. So all of the targets has like already set aside target docking threshold. So a hit molecule was a molecule whose docking threshold was less than the target threshold. I think it's a little bit confusing, but let me explain. So the docking score measures the binding energy, and you want that to be low actually. So a lower binding energy is good. It means the molecule is going to be stable. Higher binding energy means that the molecule is going to be. It's kind of like confusing, but I think like the best way that is negative on the energy measuring. So you want the docking score to be less than that. And then the curate is like, yeah, you want it to look like existing drug-like molecules. So you want the curate above 0.5. Then the synthetic accessibility, you want it to be less than 0.5 on this scale, meaning that the molecule is kind of like easy synthesizable in the lab. And then the similarity is just like how is it similar to your training data set. So you want, if it's too similar to your training data set, it means not that different from the existing molecules you have. So you want, so that there's the similarity is more or less like it's kind of like a cosine similarity that you measure between two vectors, and then you want it to be as low as possible. So in this case, I think they use like threshold of 0.4. So you want it to be less similar, so that's kind of new molecules. So we measure two things mainly. So it's mainly like trying to measure the percentage of hit molecules from the 3,000 molecules you sample, and also the mean docking scores. Like you want this to be a good value. So that's kind of like what the two metrics that you were following from this paper. So now this is how the results come. So this paper is called the technique that is in the paper is called mood. It's kind of like a diffusion based model that has some sort of a constraint that allows it to be able to sample out of distribution, out of the training set distribution. So they have like they have some sort of constraint there that encourages sampling out of distribution. And then here we have like the different versions of our models. The RL includes the ones that were the ones after RL fine tuning. And then as I said before, the ones with P are the ones in which included the perceiver. So we're actually quite happy because you can, so like the both are kind of like the ones with the always like the best scores. And from what we got, like our results were quite competitive. Like they kind of like get like actually like getting much better than for them on few of the targets. But overall, the results were quite competitive. So this is what the docking scores. and then ask is the one at the bottom, and then you saw like, but you also have like few targets on which, especially I think the last two where they kind of like do, yeah, they do way better than our model. We're kind of like, yeah, so we're kind of on the right path for this. And then the final result here was the percentage of hit targets as well. So you kind of like also doing competitive on like the first few three targets, but then they do like way better on the last two ones, especially the last one, the 5HT1B. But overall, like, yeah, so we've been able to like generate this model and fine tune it to generate molecules like with properties you want and generate potential hit targets. So the idea is that these hit targets are kind of like what you will suggest to a chemist for a specific target to do further analysis on it and further experimentation. So that's kind of the whole idea of the research, is to be able to find these hit targets, which can then be further studies in the different screening stages of for the drug discovery, and then analyze like different other properties. Yeah, since it's a paper on molecules, so I had to kind of like show a little bit of some of the molecules we're generating. So like the left column, these are just the molecules from the data set on the left, and then these are some of the molecules. These are like the same molecule from the data set, not the same molecule, but the molecules from the pre-trained model, and then finally the molecules after fine-tuning. I think that the main thing you can notice, like for all across all of them, like the docking score is increasing. And also the most important thing is like the molecules have like good QID scores, and they also look like how molecules look like. These are how molecules look like because they look like the ones in the data set. So that's kind of like the main takeaway. Okay, so the ongoing work. Yeah, so you kind of like, so as I said before, like the paper was presented as an ICML workshop, and then now we kind of like, now we have like the proof of concept. Like we know like, because the main challenge for me, as I said initially when I started working on this project, was finding this right tokenization. So now we know like the safe tokenization works well. If you have like this proof of concept, so the main stuff we've been doing now is like scaling the model. Currently, like half a model with around 180 million parameters with around 512 embedding dimension. So that's kind of the current work we've been doing, has been scaling the model. And also what we'll be experimenting on is having a latent sequence length of 1. So we want to be able to like take a molecule and have an embedding and have a latent space that has just a sequence length of 1 and just has an embedding dimension. Then the idea is to also experiment if the different embedding dimensions affect the properties of the molecules. Initially, when we tried having a latent sequence length of 1, we had a lot of training instability, and it was mainly due to the variance term in the variance term of the VAE loss function in the KL divergence loss. The variance was always like exploding, so that was making it difficult to train with with a latent sequence length of 1. So currently, what we've done is applying clipping the variance term, and since we've been able since we started clipping it, we've been able to train much larger models using latent sequence length of 1, and that's why currently now you have like our current model is like 180 million parameters, and then I feel like we could scale bigger. I feel like now the challenge we're having is just it's mainly around the training on the infrastructure and having to babysit the information and how long it takes to train. But yeah, that's kind of like the current work we're doing now. So trying to scale the model as much you can, and also see that how scaling affects the properties and also investigate about the latent sequence length and the different embedding dimensions in the latent space. And then the main goal, like the dream is to have this. So ESM is a model from Google, or from, am I saying Google? From Meta, Facebook. So generally proteins, I didn't talk about proteins, but proteins are generally presented with what you call amino acid sequences. So proteins can be presented using amino acid sequences, and because they are sequences, you can also use sequence-based model for them. And there's really been a lot of work in this area. So currently you have like the ESM model from Meta, and also and also a variant of that called the ESM4 model, and there's also AlphaFold from DeepMind. So these models are going like the state of art in structure prediction. So literally what they do is like they take an amino acid, which is a sequence-based representation of a protein, and they're able to generate a structure for that specific protein. And with this, so yeah, so that's kind of like that's it's kind of like a it's kind of a game changer in this field, because now the idea is like if you can go from amino acid sequence to the structure of the protein, then the goal, what you want, is to use this structure information as the constraint for our models. You want to have this as input. You want to have this as input to our encoder, and let that map to the latent space, and then we'll be constraining our model directly on the structure information of the proteins. And then the idea is to be able to generalize to multiple targets. So rather than always fine tuning and searching for a specific target, are we able to, if you include this structure information in our model, is it possible that in the future you could just take a new target and just pass it amino acid sequence to the model, and just output a target that fits that model? And so that's really the dream of what we're trying to do, to be able to have this model that can generalize to multiple targets, and you don't have to always fine tune and search for a unique target. Okay, yeah. So exactly like this, what I'm trying to explain here. So I have like an amino acid sequence of the protein, pass that to ESM model, and get some protein embeddings, which then enters into the perceiver layer of our model, and then finally get a Latin representation, which gets decoded into a new molecule that will have the desired properties. And then in that case, you really only have to fine tune the perceiver layer, or probably the mean and the log but you mostly have to fine tune these layers. And then we use like the pre-trained ESM model, and also the pre-trained decoder of our model. Okay, thank you. That was short and brief.
Thanks a lot, Ulrich, for the awesome presentation. That was really, really cool and also easy to understand, at least for me. So with that, is there any questions? So I think I will just like look at the chat and see if there's any question going from top to bottom. Okay, no questions for now on the chat. Let me just type something quickly. Just give me a second. Cool. So if there's no question for now, let me ask some questions that I was wondering about. So I guess like the very first question, kind of going way back at the beginning of this presentation, is the choice of focusing on sequence encodings of your proteins, right? And so you mentioned how all of these various ways of encoding the proteins. So some of them are better than others in terms of maybe the uniqueness of the encoding and so on. But I don't remember if you mentioned how, if your safer one produces indeed unique encodings. So like one of the issues that you always get when you take a type of data structure, a type of input that has some structure. Let's say for like a graph-based input, and then you can transform it to a different type of structure. Let's say like a sequence input. Then you can have the uniqueness problem usually, and then now your model or your transformer now has to learn that for all forms of that input that still corresponds to the same model, it needs to learn to be invariant to that. But it needs to learn that the model is not by definition already invariant to those variations. So I'm wondering, why did you go with the sequence type input instead of, let's say, like a graph-based input, given that the molecule is indeed a graph?
Yeah, I feel like initially, I feel like it was mainly like, as I said before, it's kind of like there's a lot of sequence-based, I mean, in terms of the data set, like you have like a lot of sequential data for molecules. Like there's a lot of data sets available with SMICE representation. But actually, yeah, actually for the representation, we did what you had to what you call standardization. So you had to kind of before converting the SMICE representation to the safe stuff. So you had to standardize the SMICE, and so this standardization is to impose a unique representation for the molecules. So it's kind of like it's good. So the standardization is kind of like putting in such a way that every molecule will only have one unique representation. Because actually every molecule only has so they kind of although the SMICE notation is kind of like general and it's kind of like no, but people have been trying to come up with like a standardization rules. That when you apply those standardization rules, if in that specific aspect, every molecule has just one representation. So that's actually what you had to do. Like the first was the input to the algorithm was like a standardized molecule to actually solve this issue.
I see. Okay, I think that makes sense, and so that kind of addresses the uniqueness issue. And so, as you're kind of explaining that, one thing that came to mind is, so once you have standardized it like that, I assume that there's also a unique way of moving from that sequence to a graph back, right?
Yeah.
To like the graph-based molecule. Cool. Then one thing that I'm wondering is, again, go look at the differences between sequences and graphs. It's like, so if there's a lot of data sets using like a sequence-based representation for all of the molecules, then I guess someone could kind of like test a graph-based one by just kind of like having a method that converts like those sequences to a graph-based representation. Is that possible, or will it be kind of like a hefty engineering work to do that?
I think it's possible, but I feel like that's kind of like really what you try to do like in the future, like really like investigate like all the possible models. For now, like most of what I saw like in the graph-based approaches was like people just having people having like to enforce like a specific structure. So literally people so it kind of like it was kind of like models where it's really developed by someone that has like good knowledge of chemistry. Like he would take like a specific fragment and then be like, I want my model to predict like which H should I modify, or which bond should I modify, or which atom should I modify, and then then he also have like a set of specific atoms from which he can select what atom to put at a specific place. And like for him to have that set is like you need like someone that really has like a good background in chemistry to like know why his set only consider these atoms and why the bonds that he can modify are just like this stuff. So it's kind of like I feel like that's kind of like the stuff that made it so difficult like to go with this model because the current ones have like a lot of like I don't know like pre-induced like constraint in them that only someone with like a strong chemistry background will be able to handle that.
I see. Okay, I guess that makes sense. So maybe like one direction in the future work is see that we have like a general graph representation that doesn't make too many assumptions about like prior domain knowledge.
Yeah. So that's the kind of like the next work because like also like that's also like compare with like all the other models that are available to actually investigate all of that.
Yeah, I think that is cool. I see there's like a one question on the chat. So Wamba asks, "What is the model used in the decoder, please?"
Oh yeah, it's still a transformer, like a next token transformer. It's the next token still a transformer model.
So using a transformer for the input and a
For
transformer
the
for
embeddings and a
the
transformer for the coding.
cool. Willie Carlos asks, so thanks for this talk. I would like to understand the role of reinforcement learning during the fine-tuning phase. Do you receive a new sample during this phase?
Yeah, so during the transformer phase, you have like so during the fine tuning, what you're trying to fine tuning is the network for the linear layer and the log variance layer, And then so when you fine tune this layer, it's kind of like so the idea is to you have this chemical space, this latent space. It's a broad area, and the idea is to push your network to find a region that will give you molecules that will bind with your target. So that's also you're fine tuning this layer. So during fine tuning, you for the same for the same observation, you sample, you decide how many molecules you want to sample, and then you use that for fine tuning. So yes, you sample multiple molecules, and then this is online. So it's kind of like you're not using like a data set. You just starting from the you sampling molecules as you are doing. So and you're fine tuning with those molecules you're you're fine tuning the molecules you're sampling because you sample the molecules and then you compute the docking scores, and then your loss function is defined based on that docking score. So the idea is to modify the area from which to sample
I see.
the latent space.
I see. So let me see if I can repeat it to see if I understand. So during the fine tuning phase, you will receive like inputs that you kind of want to produce, so like target protein inputs, and you kind of want to produce a protein that can dock to that target effectively. And the protein you receive as input during the fine tuning phase is not necessarily a protein that you have seen during training. Right? So it's like it's like a new sample protein that you are receiving. And so you kind of want the output protein to kind of like be able to effectively dock to that input protein. So the way that you are going to now fine tune your model so that the latent space it outputs or that it represents is latent space corresponding to good proteins which are very good at docking to that input. But you don't have a target, you don't have examples of that. What you do have is like a metric for kind of like determining how good is the docking for that output molecule. So you cannot use the same training approach that you use during pre-training because during pre-training you have the data set, but during fine-tuning you don't have the data set. So you are going to use that docking
Yeah, the
quality
docking
metric,
tool. Yeah,
that docking tool, to measure the
it's-
quality of the docking of the produced protein, and then use that as your reward function to then update your model by using like a loss function, like the reinforced loss, for example, where you kind of like want to maximize the probability that the output maximizes the reward you get. Is that
exactly.
kind of the idea?
Yeah, that's the idea. Just one minor correction. Just one minor correction. What you're generating here is molecule, and the target are proteins. So that's just the kind of like the
Oh, I
so the input
see.
is,
I
yeah.
see.
So the input is a molecule. So the idea is to generate a molecule that binds to a target that is actually a protein.
I see. Okay, that is
Yeah,
actually, yeah, that clarifies this a bit because I was going to be wondering like how, because like a protein would be like a whole bunch of molecules, right? And how exactly are you
yeah,
now kind of representing that in your model?
yeah.
But
So
it makes
yeah, so
sense that
yeah, the protein is supposing the living organism in us, and we are generating a molecule that should affect that living organism to cure its disease.
makes sense. Cool. So I hope that answers Willie's question. So going back to Wamba, so she asks, let's see, when the
Okay,
perceiver
I think
is
she means the
sampling.
perceiver was into shipping. Okay.
Yeah.
Yeah, so the perceiver is like it's generally like a network layer that is used a lot in that is used a lot in like in transformer architectures. I think the goal of the perceiver is that it can map input from different dimensions to different dimensions. So you can have an input that has like dimension n by e, and then you have the output has dimension ls by le. And then these are generally used like in multimodal architectures. Like if you're going to build a model that has like that will take like images as input, for example. If you have like a language model that can incorporate images, you will need an encoder for your image representation. But then the output representation from the output embeddings from the image doesn't have the same dimension as the representations for the normal text. So you need a perceiver layer that maps that input to that dimension you want. So the idea for the perceiver, for us testing this perceiver, is that as I was saying, like in future work, we want this input to be protein information, and we'll be using like a protein encoder. In this case, which is an ASM, which is going to be the ASM model from Meta, and that ASM model will have its output embeddings that has the dimension for which it was trained for. So we need a perceiver layer that then maps it to the dimension of the dimension for which our molecular generation model was trained for. So that perceiver layer we try to capture just the information we need and then map it to the dimension we want. So that's the idea of a perceiver layer. So it's generally just a network layer that is used to mesh together different modalities in different networks.
Yeah.
Yeah, it's a projection layer, exactly.
Nice. Awesome. Then moving on to the next question. So Futse asks, so thanks for the great presentation. I usually see graph representation for genes problems and was expecting a GNN, a graph neural network, to help in this problem as well. Is there a reason why this approach was not investigated? Okay, so basically, sort of like similar to the question I was asking earlier.
Oh yeah, I think I kind of answered it a little bit as well. But I think also the issue is like this approach, we started this research also being too motivated by the idea of using like the structural predictions from ASM4 and AlphaFold, which are also which are also sequence-based model that end up generating structures, 3D structures. So I think the whole idea already like shifted us already towards the idea of going towards a sequence-based model. I also think was, as I said earlier, it was kind of just fitting because currently like, most of the graph neural networks at the moment generally requires sort of prior domain knowledge. It's kind of like what you're going to investigate now in the current world. I just investigate all those models because like for now we only compare the results with the results from that other paper, and we literally just took like the result they reported there, like the best result they reported from all the models they tested in that paper. But obviously, we also want to try out some different implementations ourselves to come in future comparisons.
Yeah, that makes sense. Nice. I hope that answers Futse's question. So moving on to the next question. So Willie Carlos asks, how do you ensure the consistency in the model such that the model is still accurate on the previous sample? I mean on scene samples in the fine-tune phase.
I feel like in the pre-training phase, what you're trying to capture is like the ability of the model to just reproduce the existing model is seen before, to reproduce the existing molecule is seen before. That's what you're training it for. But the main thing you're training for is just its ability to generate molecules. So it's kind of like we don't really want to have consistency. The idea is that we want it now to generate only molecules with specific properties. So for example, your pre-trained model could generate valid molecules with good docking scores or bad docking scores, but that's not what you want. When you want to fine-tune it, the only thing that is informing you is like the property you want to optimize. In this case, is the docking score. So if at the end you'll only be generating good docking scores, so you're actually shifting the distribution of the molecules when you fine-tune, because at the end, after fine-tuning, you shift it to the distribution of the properties you want, or the range of properties you want. So you can't really you don't preserve at least consistency in that sense, in my opinion, if I kind of like understand the question.
I guess that makes sense. And also, if really means consistency in the sense of for the same input, you kind of like one or the same type of input, you want the same type of output molecules, then I guess you also don't want that because you were kind of like wanting to have diversity in your in the molecules produced. Is that correct? So you actually don't want consistency in the molecules produced.
Yeah,
Just
and I
one
think
molecules
also
that satisfy the quality stuff.
yeah, and I also feel like also that's also actually, but it's also actually that's also actually a very good question actually, because for now in this case you're only looking at the docking scores, but you could actually like add different terms to the reward function that actually ensures this. Like you could put like a similarity metric between the initial molecules and the output molecules to enforce that consistency if you want it to just get a good docking score without changing too much from the original molecule. So you could add that to your reward function. So that's kind of like, yeah, that's actually just, so the way to do it is just be like slightly modify your reward function to include this property in the reward function. We didn't do that because we're just happy like the model was only generating like a good QID scores. Like that's, I mean, that's the main thing that motivates us. Like the likeliness to look like the likeliness with the existing drugs. So obviously that would be like a straightforward way to do that. Just modify the reward function. And I think that's also what like generally makes these things challenging, because most of the time the reward function, like in the pure sense that the reward function will not just be one property. It will be like a combination of so many properties. And then the challenge becomes like, how do you weight all these properties? Like which one has like a bigger scaling factor compared to the other?
Yeah. Yeah, the thing that makes sense. That would be an interesting thing to test in the future when you incorporate those multiple properties in your reward function and how you weigh them in terms of their
Yeah.
effect in the reward function. Nice, nice. So the next question comes from Gaye. So thank you for your good presentation. Same question as Futse. I will add, could you explain more which function you are trying to optimize?
Okay, I think that goes like, yeah, that goes right to the beginning of the slide. So as I was saying, like whenever we're generating like a new molecule, there's what you call like there's that molecule, in order to be able to cure like a disease, that molecule needs to affect. So when there's a disease, in order to actually find a cure for that disease, the scientists need to identify which organism in the body needs to be modified in order to cure that disease. So in order to do that, scientists identify what you call targets, and these targets are generally are generally proteins. And then so literally like in this world of the drug stuff, there's literally like if you go online, you see like a bunch of target proteins that have been identified, and people are doing research trying to find molecules that will bind well, trying to find molecules that will modify those targets. And then in order for a molecule to actually affect the target in the way we want, that molecule needs to be able to bind well with that target. And the way for us to, because we can't know, the only way to do to know if it binds to the target, maybe we have to take someone and test the drug. But you can't just test the drug on people without actually having predicted as much as possible the effect that that drug will have on the person. So the process of trying to predict in the way in which a molecule will bind with your target, which is a protein, is what we call molecular docking. And the way molecular docking is done is through a bunch of physics simulations, and it's literally just brute force. So it's kind of like a bunch of computations. Like you will take a molecule, take its representation, take the representation of the protein, and try to find all the possible combinations in which these molecules can bind together. And each of these configurations is what it's called a conformation. And then from there you will measure the energy, the binding energy, and the best one is the one with the smallest possible energy. And then that becomes the conformation with which that molecule will bind to that target. And then different molecules binds better compared to others. So what we are optimizing is that what we call that the docking score. So that's what we're trying to optimize. So literally it's not something we control. So what we do is that we generate the molecule, we get the protein information, and then we give it to this tool that does the docking for us. In this case, we're using what's called AutoDockVina, and it does this physics simulation, and it tells us at the end that this is going to be the docking score of this molecule, and we just get that number, and then we try to use that as our reward function, and then we try to modify our model to get the molecule that next time we give a better docking score.
That makes sense. Yes. Hopefully that answers Gael's question. So actually, as you were kind of like explaining that, so you mentioned, so in your case here, you're trying to kind of have molecules with the highest docking score, but in the physics simulations, what they're trying to find is molecules with the highest binding, or was it the lowest binding energy or the highest binding energy? What is the
Okay,
correspondence between those two metrics?
no, it's a straightforward. It's a straightforward formula. So the docking score is like There is a formula that's so the docking score is directly proportional to the binding energy. So the docking so it's just like so both terms are used interchangeably. So the docking score is
Yes,
kind of like equals to some constant times the binding energy times some negative values, just like so both stuff are generally used interchangeably. So a good docking
I
score
see.
corresponds to low binding energy.
I see. Okay, that makes sense. So minimizing one is the same as minimizing the other one in terms of optimal parameters.
Yeah.
Good, good, good. Actually, also, before going to the next question, just another conflict thing that this made me realize is so like you mentioned how this evaluation function, the way like this tool that calculates the docking score, is a very expensive to compute. So given that, I'm wondering if you consider trying methods from population-based algorithms, right? Like things like quality diversity or evolutionary methods, because a very big aspect of those methods is like when you have an evaluation function, a fitness function that is expensive to compute. So you have very few functional evaluations you can do. How do you effectively search or move in your search space to find the best solution? So I don't know if
Yeah.
you've considered
Okay.
that
Yeah. No,
or
that's a very good question. I feel like the first part of the what we've done so far in the research, the first part was mostly a lot on the on finding the right the best representation we could do to be able to generate molecules. So I think like a lot of the efforts was really put into that to kind of like build first of all get like our generative molecules model, and then the next phase was going to go into the fine tuning. So in terms of the fine tuning, we haven't explored as much as we could explore. But obviously, yeah, I think like that's kind of like the trend really is to have like a actually like people have tried like having like machine learning models to approximate the docking. There's actually a model for that called DeepDock, but still they're not as so far the machine learning models are not good as as the physics based model. So they're not yet good for they're not good as the physics based model. So that's why we didn't use that. And then like yeah, so and then like the population based approach is probably like the that would be like the easiest approach. Like probably just have like something that approximates the result, and then maybe do the docking like just not every time, like maybe once in a while, and then most of the time just use like the approximate, like use an approximate for that. Yeah.
yeah, yeah, that makes sense. Um, cool. So the next question from Wamba. What is your intuition in understanding why the mood model outperforms in the last two molecules when you were showing your results near the end? You had
Yeah,
like,
so
I think the last molecule had like
yeah, like
18. It
that.
was a huge difference.
Yeah, I think the mood model was just like is so the mood model they have what they call like out of distribution sampling. So they have like they have this thing that encourages it to actually sample out of distribution in their loss function, and they use a diffusion based model. So I think probably that's why they kind of like they actually good in sampling like stuff that are not out that are not in the distribution. Like so maybe that's probably the reason why. But then also at the same time, like our current model, like the one with everything is it's a very small model. So probably hopefully when we scale the model, like what we plan to do in the future, we can get better scores. But I feel like the main thing like in the mood stuff is the fact that they have this out of distribution parameter.
I see. And actually, so you just mentioned that maybe increasing. So the mood one is like it's larger parameters than the one you have right now. Um,
Okay.
and do you of like know at the top of your head, or if you have it in your slides, how larger it is? Uh,
No, no, I don't have
it's
my
like
mind. Actually,
others.
actually what I didn't mean was like the top of. I wasn't that they have more parameters. It was the fact that they have like their design has has a specific parameter, like has like a
Out
like
of
in their
distribution.
reward function that has something that encourages it to sample out of distribution. So that's kind of like what the mood stands for. It's like molecular out of
Okay.
distribution stuff. So it's kind of like for now, like our model is literally just like trying to like our generative model is literally just trying to learn our distribution and kind of explore that, but they have like something that pushes stuff to go out of distribution.
Okay. I see. I guess then kind of incorporating ideas like that in future versions to handle out of distribution is
Yeah, I think to
buttons.
encourage, yeah,
Makes
and that's
sense.
yeah, to encourage auto distribution. And you said that's actually like what you want to do. Like you want to be able to get something that can give you molecules you've never seen before.
I think that makes sense. And you also mentioned something there that maybe kind of like increasing the size of your models will hopefully could give like better and better results and maybe be competitive with mode in like those proteins which it is currently struggling on. But I also saw in those graphs, it seems like the general trend was that as you increase the parameter size, like the size of the model, actually the performance was decreasing. I'm not sure if I was saying wrongly. Like I saw that the smaller model was having in general better performance than the larger models. If you maybe go into any one of those plots
Yeah, I think that
or
there's
of
something.
those maybe.
I think that there's some. Yeah, I think these are kind of quite. I think, but I think that the issue here is that this yeah, in this case, because these results are having like I think it's here is because we're experimenting with the latent sequence length of one. So imagine like you have this molecule that has like a latent sequence length, like this molecule has maybe 100 tokens, but we're trying to map it to just one token. So I think so for now that's the issue. So for now that's why like when you make it bigger, it actually seems like the performance is not scaling well. Yeah, but yeah, so this is what we're still really investigating. Like how to get this scaling. We're trying to see like if is it possible to actually just represent it just like along the embedding dimension. But then also like if you think of it like I think that not the right thing to do because like you're averaging all that sequential information in just one token.
Yeah. Yeah, there's definitely something worth investigating. Maybe also, if you go back to to your model map, to yeah. So like also like saw here, you are outputting mean and standard deviation, and then you're kind of like sampling from that to get your latent representation. So that's because of pretty much assuming that you are uh, they're
Prior
kind of like
distribution is
yeah, right. Like kind of assuming like a Gaussian distribution on your latent space, and that's a very very strong assumption, right? Like that is probably very unlikely to be the case. So like I'm wondering if, for one, that could be one of the reasons why, as you're increasing your model right now, you're getting more and more problems because you're just increasing the size of that space in which you're sampling, and so you are probably more and more getting samples that are just degenerate, samples that are not like really part of the latent space. Because I guess so you have your n-dimensional vector, and then you're kind of sampling each element in that vector following that distribution. So maybe that could be a hypothesis there. And if that is the case, then maybe so one thing that I had when you mentioned this section was um, one way some people handle predictions that are stochastic based on some hidden latent variables is by adding a latent variable instead of predicting mean versus standard deviation, they just add like a random latent variable. So the random latent variable is what they're going to be sampling from a Gaussian distribution, and then they're going to concatenate that to whatever is the uh, whatever your model outputted, and that is going to what will form your latent embedding, and then you pass that to your decoder. And
okay.
so the model will then learn to assign the randomness to the to the random variables, not to your model prediction.
Okay, that's actually okay. Cool. That's actually like
Yeah,
a nice idea. Okay, thank you.
yeah,
I will test that.
yeah. Cool, cool. Let's see. Is there any other question? Oh yeah. So Futse asks, multiplex graph. Oh, she's just giving a suggestion. So multiplex graph
Okay.
representations could be useful.
All right. Thank you, Fute. It's noted.
Awesome. I think that is pretty much it for the questions. Um, are there any other last minute questions for Ulrich? If there's no more questions, then thank Ulrich again for coming by, giving us this awesome presentation. Maybe this is going to be the few first steps to one day be able to generate drugs that give us superhuman powers or something. After curing diseases like cancer and stuff. So this is really cool work, also in a field which is really important these days. So yeah, thanks very much for the presentation.
Okay, thank you guys, and thanks for everyone who made the effort to be there this Saturday evening. Thank you. Have a nice
Yep.
weekend.
So, thanks. Bye bye, guys.
Okay, bye.